as well to my talk, the second one today, about unleashing confidence in SQL development through unit testing. Robert, where is he? Just said, and this is a good cue, the hard challenges nowadays are not necessarily model building, it's more on the data engineering side. So this is great. Let's talk a little bit about data engineering then. About me, my name is Tobias Lampert. I am an analytics engineer in the business development, business intelligence team at Lotum. I used to be a backend developer in my early career, and 8 years ago I started focusing entirely on the data space. I work at the intersection of data engineering, data science, data architecture, and data platforms, which is great because at Lotum there's plenty of stuff to do in all of these areas. So who is Lotum? Lotum is a mobile game development studio. We do like mobile games, and we're located in Bad Nauheim, a little bit north of Frankfurt, with 50 employees at the moment. The business intelligence team, which I'm a part of, is just 3 people. And all the games we created so far have 900 million downloads combined. These are our main games at the moment. Is anyone playing any one of those? Oh, Robert does. What are you playing?
I think I played 4 Pigs 1 Word.
4 Pigs, yeah, amazing. That's our biggest one. And we just released the newest game called Classics, Word Games and More. Just released that in October. Check it out. So analytics engineering at Lotum. At Lotum, we have this fairly standard ETL pipeline. We collect tracking data from all the players in our mobile game. So every interaction the players do, what they clicked on, what they saw, all the actions they performed in the games. This creates tracking events. We collect that. We collect data from some external data sources. And we store that data in a staging area. And from the staging area, it undergoes a series of transformations to be stored in separate tables in our data warehouse. And from the data warehouse, we power all the analytics which drive most of our business decisions. The tracking data we collect is about 300 million events per day. And the transformations we do from the staging area to the data warehouse is done by a few pretty complex SQL statements. And this pipeline obviously is evolving. We need to make changes. We need to fix bugs. We need to make additions and extensions all the time. And every time we change something to the SQL code in this pipeline, there is the question, how can we make sure the pipeline produces the expected output after the code change? Because there is one scenario we definitely want to avoid. Since the information in the data warehouse drives our analytics, which then drive a lot of business decisions, we don't want to be in a situation where we make a small change, maybe just a one-liner, looks tiny, looks harmless, and that introduces an error. But the error is not noticed immediately. The error is noticed weeks after the code went to production, and the data already has been compromised. And it also, with the broken data, maybe even led to wrong business decisions. And this situation not only leads to bad business decisions, but it leads to a situation where we need to costly backfill and repair the data, which is very time-consuming, lots of effort, and maybe even very expensive. So how can this be prevented? And it can be prevented by testing the SQL statement. So why does testing matter? Testing matters because if you test your SQL statement, you can ensure it is accurate and reliable. It produces the exact output you think it should produce. By testing the SQL statement, you can also make sure it meets the requirement and specifications. And by testing SQL statements, you can detect errors very early in the development cycle, ideally before the code actually reaches production. Also, testing enables you to catch those stealthy errors, which usually go completely unnoticed. After all, testing makes sure the data is trustworthy, and that's what every data practitioner wants, producing trustworthy data. So I talked to a lot of people over the years about testing SQL statements, and most of them say, yeah, of course, we test our SQL statements. But what they mean is usually a very traditional approach that goes about like this. They have snapshots of their production data somewhere in the database. They take snapshots, and they run these snapshots, execute the SQL queries in their query engine, and these SQL statements then produce results, which they store in temporary tables. And then they have another snapshot of a live result table, and they compare the results of that test run to the live result tables. And this can be hundreds, thousands, sometimes millions of rows of data, just to make sure the statement behaves as it should be. And they compare the results. Maybe they want to make sure there has been no change at all, so it's a one-to-one match. Maybe they just want to know if the assumptions about the data still hold, if the value ranges are the same, if there are no unexpected null values showing up, if the row counts are still the same. But all in all, oops, one too much. All in all, this is very costly, very elaborate, and usually very expensive and slow. It has also the disadvantage that it is stateful. So you need to have the test data you want to work with in your database. The tables need to exist, and it relies on certain states of your database. You need to duplicate your production data into a test table, test environment. So you need to have double your data. It takes twice the amount of space. It has very limited scope. Because you can only do testing on data which already exists. So you can do tests on historical data. You cannot do testing for scenarios which could happen in the future, but for which you don't have any live data yet. Also, it is very difficult to isolate. So if something goes wrong, this testing approach will tell you, well, the result table and your actual live table, they don't match. But what the actual problem is may be very, very hard to pinpoint. So it's very hard to tell from the differences in the data what the actual problem in the code is which caused this difference. Yeah, it's non-atomic. That's what I just said. And it can be, as I said, it can be very slow because the testing is done on lots and lots and lots of data. It takes a while to do these test runs. And this also can be really, really expensive. There is an approach which I favor which doesn't have all these disadvantages. And it's called unit tests. Unit tests, for those of you who don't know what is a unit test, let's have a look at Wikipedia. Wikipedia says in computer programming, unit testing is a form of software testing by which isolated source code is tested to validate expected behavior. That's what I want. I have an SQL statement, and I want to test if this SQL statement behaves as expected. And also, a test case, according to Wikipedia, is a test case describes the expected behavior, and that is the output of the code under test for a particular setup, and that is the input. And that is exactly what I want. I want to test if my SQL statement produces the exact output which I expect for a given input. But I don't want to do this for a huge database table. I don't want to do this for 1 million rows. I want to do this for a very tiny, tiny set of well-defined input data. So unit tests for SQL statements. How does that look like? So basically what we need to do is we have to construct a test case. A test case consists of two parts. The first part is the input data. The input data for a test case would be 0 or more rows from the tables your SQL statement is referencing. And you have the expected output data. And also that could be 0 or more rows. So it could be 0 rows because obviously for a given input, the SQL query may be returning nothing at all. And it could be like 0 or more rows, depending really what the input is. What you can then do is run your SQL statement with this input data which you defined, and then compare whether the SQL statement for this given input returns the output data which you are expecting. So you're comparing your expected output data from the test case with the actual output data the SQL statement produced when it was fed with the input data from the test case. So how should a test case for an SQL statement look like? There's a couple of properties which I really want how my test cases should look like so that they're really efficient and nice to work with. First of all, they should be atomic. And that means they should focus on a single aspect of the functionality of an SQL statement. It doesn't really make sense to test the entire functionality of the SQL statement. No, I want to focus on a little part of the functionality only. I'll give you some examples later. Also, they should only use required fields. So I want to test a little bit of the functionality, and maybe for this little bit of functionality, I don't need all the columns in my database table. I only need a few of them. So the test case should only include those. And I want my test case to be compact. So I don't want, as I said, I don't want to do this on hundreds and thousands of rows. I want to do this with as little rows as possible. So I want a test case that works with a row, just one row or maybe 2 rows of data only. So to sum it up, we can say a test case should only have as few input rows as possible with as many empty fields as possible. OK, so let's write some tests then. As we all know, it's the year 2024. AI is the big thing. If you believe the hype, nobody is writing code by hand anymore. Probably none of you do. So we use GitHub Copilot to write the tests. AI code assistance, AI pair programming is the big thing now. GitHub Copilot has this nifty little feature where you can write /tests in the chat box. And it says, generate unit tests for the selected code. So if you open a SQL file and write /tests, it says it will create some unit tests for you. Unfortunately, when I tried this, GitHub Copilot was not really willing to cooperate. It said, as an AI programming assistant, I can help you generate tests for your code. However, the code you provided appears to be SQL code, and writing tests for SQL code is not a common practice. So writing tests for SQL code is not a common practice. That's what it said. Obviously, that was pretty disappointing. But it had a point. It actually is not common practice in most companies out there. Only very few of the companies I talked to over the years actually do unit testing or actually tests for their SQL code. And I say, but it should be. So I'll give you a good framework today how you can do testing for your SQL codes. So when we started doing this at Lotum, and I must admit, we didn't test our SQL statements from the very beginning. We obviously, over time, we felt there was a need to do this. So when we started doing this, we had some requirements. We wanted the test cases to design in such a way that we do not need to persist the test data in the database. We wanted to be able to execute a test for our statement on the fly without creating any tables first, without duplicating any data, without writing test data to the database first. But we wanted to do this in a production-like setting. We didn't want to have some unrealistic test environment. We wanted to do this as close to the production database and query engines as possible, ideally running the tests in the production setup itself. We wanted the test definition to be independent from our SQL code. We definitely did not want to modify our existing SQL so that they're testable. We wanted to be able to define test cases in separate code that are able to test the existing SQL code. And as I just said, we wanted to be able to define our test cases as code. So how did we do this? It's actually pretty straightforward. So we represent database tables as Python dicts. So if you look at this sample employees table here, it has 3 columns, 3 rows, which are representing employees with a name, a department, and a salary. And you can use Python dicts to represent this exact information, where the key in the Python dict represents the database column, and the value, the value of this column. And if you do this for multiple rows, then you basically end up with a list of Python dicts which contain this exact information as it is in the database table. So let's have a look how this looks like with an actual SQL statement. I have this sample SQL statement here, which doesn't do much. I mean, it's selecting data from an employees table. It's grouping the data by department to calculate an average salary. In order to test this code, well, what would be kind of the most simple way, or the simple case to test this code? We would need 1 row of data, basically 1 employee of a given department with a given salary. And if I would use this as input for this SQL statement, this is what I would expect as an output. I would expect 1 row with exactly this department and exactly the salary, which I used as input, because if I have 1 row of data, there's not much to do. For an average calculation, you get exactly this value back. Obviously, that is a test that really doesn't make sense. It tests the most basic functionality of this statement. So if I want to go 1 step further, I would be able to actually test if my average calculation really works. I would need 2 rows of data for employees from the same department, but with different salaries. So I can check, OK, first thing, my expected output would be there's only 1 row in the output, and not multiple rows and not 0 rows, exactly 1 row. And the average salary, which I calculate, is actually the average of this 150 value. So this is how I create my test cases, going from a kind of very simple case to more complicated cases, only focusing on a tiny part of the SQL statement. In practice, things aren't that easy, unfortunately, because nobody really has database tables with only 3 columns, which contain only 3 rows. In practice, you have database tables with dozens, maybe hundreds of columns. So in order to test those, we need a little bit of a different approach, because in order to test those, obviously, you need to provide a value for each of the columns. But as I said, I want my test cases to be atomic. I don't want to provide the values which aren't really relevant to the test I'm doing over and over again. And the solution for this is, at Lotum, we define default values. So for instance, for this employee, we say, OK, this is our default employee. And we use this default employee with all these values to derive test cases from it. And this derivation only focuses on parts of the data that need to change in order to test the functionality of the code. Most of the values can stay as default, and only a few of the columns need to change in order to make the test. I'll give you some examples. We use dict merging for this a lot in Python. This is a lesser known technique in Python. I don't know who's familiar with dict merging. Somebody ever heard of dict merging? No? OK, well, then you learned something. OK. Most of you learned something very interesting today. With dict merging, you can combine 2 Python dictionaries where using the pipe operator. And the keys in the second dictionary will be added to the first dictionary. And if they already exist, they will be overwritten. And we're using this to take the default employee, which is a dictionary, and then on the fly replace or add some of the values which we want to change without writing the default values from the default employee over and over again. So this is how we can create really simple and compact test cases which only focus on a few changed fields. So for instance, the first one would be kind of a continuation of the test cases I already shown. We have 2 employees with 2 different IDs and 2 different salaries. And obviously, they also have addresses and names and email addresses, but we don't care for this test. So these remain all on the default side. And you can iterate on top of this. Then we have a test case, for instance, where we have 2 employees with the same email address, or a test case where we have a hire date in the future. And then you can basically think about everything that could go wrong. I mean, add a null value there, or try to build test cases with employees from multiple departments, try to add 0 values, negative values. Basically, these can all be separate test cases testing isolated functionality of the code. But this is only how we define test cases at Lotum, and that's only kind of one half of the whole concept. We also need to verify whether this input data and the expected output data actually matches the produced actual values from the SQL statement if we give it this input data. And how can we do this? How can we, as I said, we don't want to persist any data in the database. We don't want to write this test data to the database. We want to do everything on the fly. And how can we do this? We do this by combining the SQL logic with the input data. Basically, we insert the test data into the SQL statement itself. And how's that done? We create some virtual tables. We populate these virtual tables with the static test data, and we then substitute the references in the SQL statement from the live tables to point to the virtual tables. Now, I'll show you how this looks like in code in detail now. So basically, we have this input data. Again, this is one employee from department 1 with salary 100. And we can represent this as SQL like this. This is, for the people who don't know SQL that well, it's called a CTE, a common table expression. Basically, a common table expression acts as a virtual table which only exists for the duration of the query itself. And this virtual table, and for the ones who know SQL, this may look pretty odd because there is no from keyword here, but this is actually perfectly valid SQL. If you works in pretty much any database and query language. If you execute this, you will get a result, 1 row with 2 columns, department and salary. It doesn't need to reference a live table. It's a self-contained virtual table in itself. And this is how we can represent our input data as SQL. And you can do this with multiple rows as well. You just need to union all the rows together. So what I have here is 2 rows of input data, and the corresponding SQL CTE would be a table with 2 rows and 2 columns as well. So and how do we inject this in the actual query? So basically, we have to combine these CTEs, which hold the test data, with the original SQL statement. Down here, you see the original SQL statement. And up there is the CTE with the test data, which I just created. We can simply combine them like this. But this doesn't work quite yet. What we need to do is we need to adjust the table references so that employees here, which references a live database table, and this is something I don't want, I want to instead use the mock data employees virtual table as my CTE here. So I basically just need to change it like this. And there you have it. This query does not reference any live tables anymore. It contains its own test data, and it can be run in the query engine and instantly returns the actual result for the given test data. This doesn't need any tables in the database. You don't need to create these tables first. You don't need to copy any data to the database first. This is all kind of a self-contained SQL statement with the original logic basically unmodified. So to put this all together, all the steps are: we define our input data as Python dicts. We create CTEs with mock data from these Python dicts. We combine these with the original SQL statement. We transform the table references so that they point to the virtual tables in the CTEs. We send this query to the query engine. We get the actual results back for the given input data. And then we can compare if these actual results match our expected results. So this is how we do it at Python on kind of the very small level. If we want to run our entire suite of tests, then obviously you need to orchestrate this a little bit. And we use PyTest for this. PyTest's pretty much the standard Python testing framework. In PyTest, you can do something like you define a test case. And what we did is we wrote a class called mockTable, which acts as a container for the input data and the output data and the expected output data. So in this case, we would define a mockTable which contains our input data, which we defined. We would define a second mocked table, which contains our expected output data. And we would define a third mocked table, which then would contain our actual output data. So this, you see here, doesn't contain a data part anymore. It just contains a reference to a mock table we created earlier. Behind the scenes, these mock table classes would do the exact same thing I just described, creating the SQL statements with the injected CTEs, sending it to the query engine, and then containing the result. And all we need to do in the end is make sure with this assertion that our expected result matches the actual result. And if it doesn't, this test would fail. This is how running the test suite really looks in production at Lotum. This is taken, I think, on Friday last week or something like this, so it's pretty recent. We have, in this case, we ran 148 separate tests on our SQL statements. We group them in several parts depending on which statements they're actually testing and what part of the pipeline they're testing. And you see here, we run 148 separate, completely different test cases on our statements in 6 minutes and 29 seconds, which is pretty quick, I think. So let's revisit the traditional approach and how my approach stacks up against it. So first of all, the traditional approach is stateful. My approach is executed on the fly, doesn't need to have any specific state of the database. We don't need to duplicate any data. We don't need to copy our production data. We just have test data, which we inject and send it to the query engine on the fly. There's nothing persisted. The traditional approach has limited scope. What we can do is basically everything we can come up with, which could go wrong, any case, realistic or not, that could put our statement in trouble, we can define it as a test case. We don't need to wait until this problem actually occurs in the live data. And if something goes wrong, this is the really nice thing about it, we know exactly where the problem is, because we test only a very, very tiny part of the statement itself and not the complete SQL as it is. We focus on very small parts of the SQL functionality. Also, as I said, you can run this in any environment. We at Lotum actually use the production environment to run our tests. And we can because it's completely stateless. It doesn't modify the production environment, and it's super lightweight. It doesn't put it under stress. You can run these tests in parallel. Multiple people even can run these tests in parallel. The database engine doesn't care. It's basically in and out, doesn't change the data at all. And this makes it very easy to handle and enables you to run this actually in a very close to production environment. Non-atomic, that's what I already said. It's very, very easy to pinpoint the actual problem in your code. And since the traditional approach can be really slow, this unit testing approach is super fast. On average, the tests we run at Lotum take 2.9 seconds each. And depending on the query engine, in our case, we use Google BigQuery. If you use a different database engine, in your case, it may be even much faster than 2.9 seconds. So Our framework, which we built at Lotum, is a little tailored to the exact data warehouse we have and some oddities we have in the data pipeline. But if you want to do something like this, you don't need to reinvent the wheel and implement everything from scratch. I mean, I encourage you to do so. It's a great learning experience. But if you don't want to, here's 2 suggestions of frameworks you can use for this. The first one would be SQL Mesh, which is kind of an all-purpose data transformation and modeling framework. It's backwards compatible with dbt for the people who are using that. And it does much more than just testing. But the testing part of it actually follows this approach where it injects mock data into the statement using CTEs. The test cases themselves are defined as YAML. So they're not defined as Python. If you're a Pythonista and want to do it in Python, that's not your thing. But they're really readable. I mean, this YAML code for the test cases makes it really and it's pretty lightweight as well. If you want to follow the approach I described, like super close, then SQL mock is the library you want to use. This one has been developed by a former colleague of mine. Hello, Thomas, if you're watching this. Very, very cool library. Supports a lot of different query engines, BigQuery, Redshift, ClickHouse, a couple more. And this is a Python library, and it does the exact thing I just described. Taking Python digs, injecting them as CTEs in your query, and you can define the test cases in Python. So this is pretty much, I'd say, the closest thing you can get to the approach I just described. So to conclude this, testing SQL statement improves your code quality. You can make sure your SQL code has the expected behavior. It minimizes errors, which is very important, and it minimizes errors during the development cycle. And I can tell you from experience, I write a lot of SQL code, and many times I wrote a statement, I thought it was finished, I'd say, okay, now I just need to write the tests. And while I was writing the tests, I realized, oops, some of these tests fail, even though I'm 100% sure the test is correct, and that is because I missed some edge cases or the statement itself is not quite ready yet. So writing the test actually is a real eye-opener and will tell you all the problems you still may have with your code. And in the end, it boosts your confidence because you don't need to do any data verifications, no expensive data comparisons anymore. If you have a test suite like this, as we have with 148 tests here, and if you see they run and they all go green, you can deploy this with peace of mind and rest assured you did everything you could to verify this statement behaves as expected. So thank you for listening. That concludes my talk. I'm happy to answer any questions. You can contact me on LinkedIn if you want to. And before I do, I just want to let you know we are looking for an analytics engineer at Lotum. So if you are a Python and SQL wizard and like to work with me on 300 million events daily in the gaming industry, let me know.
Awesome. Thank you very much. Yeah, pretty cool approach. Yeah, questions? Yes.
Hi. Thanks for the talk. I basically have the following question. Maybe you mentioned it, but yeah, I didn't get the details. So when you write unit tests in Python, so normally you have a very small function which returns the value, but in SQL, maybe there is a notion of a function or something, but how do you deal with very huge SQL queries? How do you split them? And also related to this question, like a follow-up, unit tests also help to write, let's say, a clean and like splitted code, right? Does it help you somehow to write a better SQL query?
I wouldn't say it helps write better SQL code. It just helps verify. I mean, this is exactly the point you're addressing. Sometimes there is no way around writing complex SQL code. SQL isn't really designed to be split up in classes and small testable chunks. The closest thing you can do is like use a lot of CTEs and try to test these CTEs separately, like try to make them behave like mini precondition tables. But in practice, you end up, and we do at Lotum, you end up with SQL code that's 100, 200 lines, super complex. And this is the reason where testing actually comes in. And this is the reason because, I mean, just by looking at the code, it's really hard for SQL developers to say, hey, this behaves as expected. And this is the reason why testing really helps you to verify that this complex code is really good. I don't say it's a tool that helps you write better code. It's just to verify that the complex code you sometimes need to write is working as intended.
Thanks.
Okay, that's easier. Yeah. I had two questions, in fact. Like, does this work with procedural language, like PLSQL? If you write procedures and you want to test these procedures instead of just writing SQL?
Like, you store procedures?
Yeah. Have you tried it?
I don't think so, because then you have a whole new layer of complexity. I didn't really think about this, but this is not what I really intended. I mean, it's basically you have this SQL code, which is a transformation. In some cases, that may actually work. But because in the end, I mean, a stored procedure is also kind of some kind of canned transformation. I'm not 100% sure, but I mean, why not?
Yeah, I'd be interested to test that, to be honest.
Any more questions? Yes, I'll be there in a minute. Oh, it takes really a minute. Oh, sorry.
Thank you for. Thank you for the talk. So you mentioned many hundreds of columns, some complex SQL queries. So how do you ensure the total coverage of your unit tests? Is it an incremental process? Have you had some moments where you thought, oh my God, we're missing so many of these tests still? Or did you do it all in one go?
Yeah, that's a good question. There is no real way to measure that you have good code coverage, because in a lot of cases, I mean, SQL statement is not functional. So most of the code actually doesn't do anything, because it's just like listing static columns. And then on the other hand, you may have a single line, like a group by or a window function, which needs 10 or 20 separate test cases to verify it's behaving as exactly. So, I mean, measuring the code coverage isn't really a thing you can do. What we do in practice is, the first approach is we start with a very simple case, and then we just imagine what can potentially go wrong. We also tried, I mean, it's AI age, we also tried to have LLMs write the unit tests for us. I mean, GitHub Copilot isn't really cooperative, but if you follow a more elaborate approach, with a very nicely engineered prompt, some of the code-focused LLMs come up with pretty good ideas on what should be tested for a given SQL statement. And it's usually something that kind of at least extends the ideas you have, and kind of if your imagination comes to a natural limit, then using AI sometimes can go a little beyond that.
Thank you.
More questions? I have a question. What was your most valuable contribution ever finding bugs in SQL statements?
The most valuable contribution, that's really tough. I mean, using this testing approach, I definitely found some ways that would have caused all major headaches in production if it went to production. Because usually this is cases where you have fan out, where you have cases where a statement produces additional rows which you don't want. And especially if you do a lot of inner joins, left joins, outer joins, it's sometimes really hard to kind of imagine all these cases where this can happen, especially if you don't know the data that is going to come into the statement yet. So, I mean, I worked for Shopify as a data scientist a couple of years ago, and we were dealing definitely with millions of rows there, and I definitely saved the company a couple of days of work repairing all this stuff just by writing a proper test.
Thank you. All right. Thanks again for the great talk.